from Wisconsin today. Ben is a PhD student there working with Shuchi Chawla, and he has done some really interesting work in auction theory, AGT mechanism design, and is going to talk about some of this recent work.
Thanks. Well, thank you all for coming. It's a pleasure to be here. And so this talk is originally geared to a sort of general theory audience. I'm guessing most, if not all of you, are more or less experts in what I'm going to be talking about, so feel free to let me know if I'm going too slow or too fast or whatever. Anyway, yeah, so this is joint work with Shuchi, my advisor, Kira Goldner, who's a student at University of Washington, and Manolis Andrakis, who is currently a postdoc at UT Austin. So we looked at revenue maximization with an uncertainty-averse buyer, and I'll tell you exactly what we mean by uncertainty-averse in a moment. So first of all, the idea is that in mechanism design, we often encounter some sort of randomness. So for a simple example, suppose we're selling just these two different items, and we have a prior with the seller. So we have a prior over the buyer's value for these two items. Then we look at them like this. It's well known that the optimal mechanism actually offers two options. Either A, you get the bundle of both items together for a price of 4, or you can choose option B, where you get the first item with probability 1, and you actually flip a fair coin and get the second item with probability 0.5, and you can pay slightly less for this, and this is the optimal mechanism. So it has this kind of strange format where there's this menu of different options you can choose, and some of them actually have some randomness or uncertainty associated with them. So this is theory, but it does show up. Excuse me, clicker word. Does show up in practice. So
there might be a little bit of lag.
I see. Okay. So for example, Priceline is this website that you can buy airline tickets from. So when I was looking at tickets from Madison to New York, I went and did this search. And you can see that down towards the bottom, we have these sort of standard results where you can buy a certain flight, you get a certain airline, a certain departure time, and so on, and you see the price. And then up at the top, they have this express deal where you don't actually know exactly when you're taking off or what airline you're flying, but you can pay less for this sort of uncertain outcome. Okay, so this sort of thing shows up in practice. And the basic format here is this sort of example. So suppose I offer you either $500 with probability 1, or I offer to flip a fair coin and give you $1,000 if it comes up heads. And which one would you choose?
I would choose A.
Yeah, most people would probably choose A, okay? So we'd say a risk-neutral person would be indifferent between the two, but in practice, we do this experiment. Probably most people would choose A.
As the gamblers might choose B.
Yeah, and in fact, you can actually reduce it, and many people will continue to choose A even when the amount is less. So this is known as a risk-averse buyer, right? Or a risk-averse behavior where you are opposed to sort of the uncertainty, the risk that you might get nothing, where you could have had $450 of certainty. Okay, and the standard model for this is what's known as expected utility theory. So this came from von Neumann Morgenstern in the early 20th century, or the middle of the 20th century, when they basically invented game theory. And their model says that for each possible outcome, you have some utility associated with that outcome. So in general, you have some decreasing marginal value for money. All right, and then you'd explain the previous example by saying that, well, if we assign a utility of 450 utils arbitrarily to $450, we might assign something like 750 utils to $1,000. Then the expected value of that second lottery, where you only got $1,000 with probability 0.5, is actually worth less to you than $450 with certainty. Okay, so this is the sort of standard model of risk aversion. But there are some problems with it. So for example, Maurice Allais, a few years later, did this experiment where he offered people either $1 million with probability 1, or the second option, where you get $1 million of most of the probability mass, but there's some non-trivial probability on $5 million, and then there's very tiny little bit of probability on $0. So you might get absolutely nothing. And it turns out that many people choose option A. Right? And this is fine. So far, so good. You can assign utilities to each of 0, 1, and $5 million, such that this would be the expected behavior. But now suppose we offer this second experiment. All right, so we offer the same outcomes, except that we move 89% of the probability mass in each case from 1 million to $0. Now, which choice should people make? Right? Well, you have a thought?
No, I'm trying to figure out what I would choose.
Well, what you would choose, what? Yeah, right. So there.
I think I'll choose C actually.
You're going to choose C. So which would you have chosen before? I guess.
I would choose A.
You choose A and then C.
Yes.
You're consistent.
Really?
Yeah,
choose
I
C.
choose A
That's
and
strange
D.
though, right?
Yeah, I
D
think
is
so.
more
Most
reasonable.
many
Yeah.
people, maybe not everybody, but many people would choose A and then D, right? Because here there's this little chance, but there is some chance you get nothing. Here the difference is almost 89% versus 90%. It's almost the same thing. But here, if you win, you get 5 million.
I'll
This is a
say
lot more
that
than
I'll be
one.
pretty flat after 1 million and I'll just maximize probabilities.
Okay. But at any rate, some significant fraction of people, some non-negligible fraction of people would make this switch. And the point is that there's no way to assign utilities to these different outcomes such that you can explain this with an expected utility theory. Okay. So sort of, I guess, the standard model within behavioral economics is prospect theory. And the assumption here is that people are fundamentally misvaluing random events. Right? So let's look at just this simple example first. So suppose we have either 0, I guess this laser's not going to work. Okay. So you either get 0 with some probability or you get some $R value. Then we'll define the weighted expectation of this randomized outcome to be this weighted utility, right? Where this would be the standard expectation, right? Just the probability of winning it times whatever utility for $R is. But we're going to actually weight this expectation according to this convex function. So on the horizontal axis, we have the quantile. And on the vertical axis, we have this weighted probability. Okay? And we're going to assume that the curve lies below the identity function so that you're underweighting random events. Okay, so this is going to give you risk-averse behavior. All right, and I'll define how exactly this works out for more complicated lotteries, but for this simple example, the point is just that you're basically underweighting probabilities. You're decreasing the probabilities. All right, and so for those of you who might be familiar with prospect theory, I should point out that actually our model is going to be a special case of cumulative prospect theory, which was put forward a couple decades later to sort of address some issues with the original prospect theory.
And prospect theory gives any guideline on what Y should be or no?
Yeah, okay, good question. So in reality, when people try to measure these things, behavioral economists do experiments, you see that Y looks more like a sigmoid function. So it actually rises above the identity function here, and then crosses somewhere in the middle, and then rises up again. So you get basically people overweight small probabilities. So in that previous example where there's like this 1% chance of getting nothing, people were really fixated on that and saying, well, there's some chance that I'm going to get nothing. That looms larger than it should in some sense. Whereas something that's a high probability, like 10% chance of getting $5 million, people somehow underweight that relative to what the mathematical expectation should be. And I can also point out that cumulative prospect theory does allow for this utility function as well. So it's a strict generalization, actually, of expected utility theory. Okay, so this is prospect theory. Now, so turning back to mechanism design, so there's been a lot of work in mechanism design from computer science perspective. So Meyerson's original paper showed that when you have just a single buyer and a single item, the optimal mechanism is a fixed price, right? Of course, it gets more complicated when you look at multiple items and more complicated settings. So there's been all this really beautiful theory that addresses these more complicated situations, but they all assume risk neutrality. Okay, so all this work assumes risk neutrality. So what about risk-averse buyers? Well, there has been some work on risk-averse buyers, including in the 80s, some economists looked at the optimal mechanisms for risk-averse buyers, but again, all of this work is assuming expected utility theory. Okay, so what about prospect theory? So the most relevant work to what I'm going to talk about is this paper by David Easley and Apriti Ghosh from EC last year, where they looked at a crowd sourcing problem, where you basically have a bunch of different workers and you want to figure out what's the best way to recruit some workers to do your job for you. And they showed that there's actually qualitative differences between the best way to do this. And if you assume an expected utility theory model, the best thing to do is basically just to offer a fixed reward for people doing the work. Whereas if you have a prospect theoretic model, the optimal mechanism might be a contest. So you only pay the person who gives you the best work. And then people compete to win, and whoever wins gets paid. Okay, so our goal is to understand the implications of a prospect theoretic type model within for revenue maximization. All right, so this is just sort of a summary of our model and how it fits in with existing models. I'll just point out that our model is a special case of prospect theory, and it also includes risk neutrality as a, if you set this weighting function to be the identity function, you recover risk neutral behavior.
Prospect theory is not a generalization of expected utility theory.
It is a generalization.
It is because you still have the, whatever you can do with the utility function, concave utility function and so on.
Yes.
And furthermore, now the probabilities also are changed from linear to, let's say, the convex.
Okay, because you can modify both.
Modify both, exactly.
Okay.
Yeah, right. So we have this, what we call a weighted expectation. So I'm indicating this with this, y subscript on the expectation. And expected utility theory has this nonlinear weight value for money, basically. Cumulus prospect theory does both.
Mm-hmm.
So you have the buyer to be risk averse, right? The seller is not risk averse.
Right. The seller is risk neutral. The idea being you're going to repeat this many times and want to maximize your expected revenue. Okay. All right. So what are our results? So initially, we're going to look at a simple setting where you have one buyer and one item. Here, we know that for a risk-neutral buyer, the optimal mechanism is deterministic. And furthermore, there's this really nice characterization of any mechanism, which gives you the allocation as a function of the buyer's value. And then there's this payment identity, which either you're familiar with or it doesn't matter. But the point is that you can characterize the mechanism exactly by this one allocation function, right? In our case, it's not clear. I'll go through this a little bit more in a moment, but it's not necessarily clear that such a thing should exist for a risk-averse buyer. We'll show that actually the optimal mechanism does have a relatively simple form, although it can be randomized. And then it's also well known that there's a gap between the welfare and the revenue that you can get, right? So essentially, the seller doesn't know the private value of the buyer. If you did, you could charge a price exactly equal to the buyer's private value, and you could extract the full welfare. But there's this information rent that the buyer earns because the seller essentially has to pay something to learn the valuation. Okay, and in our setting, with an extremely risk-averse buyer, that gap disappears. All right, so I'll talk about all these results in a little bit more detail in a moment. But everything I just told you about this optimal mechanism that we come up with for this risk-averse buyer depends on knowing this weighting function exactly, which is an unreasonable assumption. For one thing, probably most of you, Renato was here a moment ago trying to figure out what he was going to choose. Probably he doesn't know exactly what his weighting function looks like. And furthermore, econometricians have actually tried to measure this in practice and found that within a population of undergraduates, so you can take that for whatever it's worth, but some people are risk neutral, some people have different forms of this curve, and it's not clear that you can necessarily assume one curve, right? So we'd like to have some mechanism, so a single mechanism that gives a constant approximation to the optimal revenue from a mechanism that is predicated on knowing the weighting function, right? So we have some feasible, some class of weighting functions that might be present in our population, and we want one mechanism that will do well for all of them, right? So we call this a risk-robust mechanism. And
sorry, you want it to be incentive compatible for all possible risk profiles?
yes, we want it to be incentive compatible and give an approximation to the optimal revenue.
Is it for the list like it's exactly incentive compatible for all possible risk profiles?
Yes.
And
yeah.
Right.
So the challenge.
So your mechanism knows the prior, right?
Yeah, you know the prior. So your mechanism knows the prior, but not the weighting function.
Just a comment about the notation there. Like it looks like in the RHS you have F inside opt, right? Which means opt is using the distribution, and similarly you also want to use the distribution,
Yeah,
right?
okay,
So you want to put an F inside there.
Yeah, so F should depend on F as well.
Yeah.
So the revenue from this one mechanism.
Because in particular, I thought when you put something in the subscript that you don't want to depend on it, right? You don't want to depend on the little y here, right? Your mechanism
Right.
doesn't depend on the little y,
So-
whereas op depends on it.
Yeah, so the point though is that M does depend on F in general. But the revenue from it is, we want to look at the revenue given this as a function of the y, basically. So, okay, yeah, so the notation maybe is not completely clear. But hopefully that's clear what we want, right? All right, so we'd like a constant approximation. It turns out this seems to be challenging basically because of these examples I just mentioned a moment ago, where for some extremely risk-averse buyers, the gap between revenue and welfare disappears, whereas we know for a risk-neutral buyer, there's this non-negligible gap, okay? But the thing is that these extremely risk-averse profiles are kind of unrealistic, right? So we make this definition. So we say that a weighting function is beta-bounded if there's a rectangle underneath the curve that has area beta. And the way to think of this is to say that for some probability bounded below 1, the weight is bounded above 0. Right? And then we show that if you have a weighting function which is beta bounded, that factor beta translates directly into a guarantee on the Meyerson optimal price.
So the curve doesn't need to be convex or anything. It could be particularly the thing that for I imagine probability 0 for everything, below beta and beta exactly.
So we assume that the curve is convex. So all of our analysis assumes that the curve is convex. I don't know that that is a super necessary assumption. But we would always want to.
True, I'd say.
Yeah. So I talked to, for example, James Wright, who is a sort of behavioral economist at MSR, and he was saying that, by the time you make this assumption that it lies beneath the curve, assuming it's convex is another small assumption. Because in reality, like I said, these curves are not going to lie.
No, but it's reasonable. I think it's reasonable.
I also don't think it's, and I'm not sure that this result depends on it. I think we should be able to generalize it. But okay, one point is that this is not a tight approximation. So if you look at this, the largest rectangle for the identity function, you get an area of a quarter. But we know that the optimal price is optimal overall for every neutral buyer. So not a tight result. But
The optimal price, like the Meyerson price.
yes.
The Meyerson price for, okay.
Because the Meyerson price,
And it's deterministic, so it's definitely IC for every.
so it's IC for everybody, and it doesn't change based on Y.
I see,
It
okay.
doesn't depend on Y.
But the only type of mechanism that's clear, the only mechanism I can think of it's IC against every single Y is deterministic mechanisms.
You could come up with other mechanisms, I think, but yeah, okay. I mean, if you think of it in terms of a menu, right? You can always just think of offering one menu to everybody. Yeah, people will probably choose different
Okay.
entries, but don't worry too much about the IC thing, I guess. But yeah.
Sorry, why do you say only deterministic mechanisms are IC?
No,
but also if you
I would see if there's any non-trivial mechanism that's IC for every Y, UY.
So let's say I give a menu of lotteries. What is the problem?
Oh, but like when you talk about mechanism, you usually think in terms of like submitting a bid and the mechanism itself choosing an element of the menu for you.
Okay.
So
but I guess it seems like you are thinking in terms of the menu.
Yeah,
so
just think of it in terms of
it's
the
not
menu.
really an issue. It's like,
Yeah, it's not really.
It's not really a constraint.
Yeah, you're right. Probably, I can't think of. I would guess that there is no IC mechanism other than the deterministic mechanism. When you think of it in this way of buyer bidding and then you giving the allocation.
And if it's like a one bidder mechanism, it's like
Yeah, one bidder mechanism I think is the same, but multiple buyer mechanism is a little different.
Yeah.
Right.
It's
use
true.
revelation principle, like where does this
Use
go
the
wrong?
revelation
point is
principle without knowing, because the revelation
don't
principle
know
need to know
why.
why.
yeah. So you might be able
Oh yeah.
to.
So if you can't also tell them why,
So
then
you might be able to argue that
yeah.
the equilibrium of the like the revenue at the equilibrium is at least.
but somehow they should know why if that's like the utility they're getting. Somehow. Okay, maybe.
I don't know, the buyers know why, but
The buyers know why, the
designer,
seller doesn't
but the
know.
designer,
So you
no.
can't give if there are n buyers, like you have to decide allocation, you can't decide.
Can't you also tell them your why in addition to your bid?
Oh, you could do that, yes.
Like,
You could, yeah, okay. So you could do that, and then
That's,
mathematically it would work out. Then there's the issue though of can people really report their Y?
Yeah, I mean, realistically, it's not
Realistically,
gonna
yeah.
Then you
So
have to do the definition.
But
the idea is if you look
Report
at a
Y.
menu, at least you can imagine somebody just choosing their favorite option from the menu.
yeah.
Modulo things I was talking with Fernando about earlier, right?
And my question is it for multiple buyers or single buyer? This
is all for single buyer.
for single buyer.
Everything I'm going to talk about today is single buyer.
Uh-huh.
This is also for a single item. So the next thing I'll talk about is a dynamic setting where we talk about 2 items, but
Nice.
always single buyer.
Just to make sure I'm not missing it. When you say approximation revenue, it's to the Myerson optimal revenue?
So no, so this is, I can't use this. This optimal revenue is the optimal revenue that you could extract if you knew Y, which is in general more than the Myerson optimal revenue.
So you can always extract Myerson because Myerson is deterministic.
Yes.
Sure, okay.
The point is that when you have this risk-averse buyer, you can actually do something with some lotteries to earn even more revenue.
So it's
Right.
opt as a function of y and f, like he wrote there.
Okay, and beta quarter is not tight because you have examples that
It's not tight because we know that for a risk-neutral buyer, this function looks exactly like the identity function, right?
Yeah.
And then the area here is 1/4. So
And
this
then-
only guarantees a 4 approximation for a risk-neutral buyer, but we know that for a risk-neutral buyer, the optimal price is the optimal mechanism. So maybe you could do something, more sophisticated with this curve and get a better approximation guarantee. But the advantage of this is that you only have to look at like these 2 points, or just measure the weighting function at 1 point, basically. Okay. So then I'm guessing many, if not all of you, are familiar with these dynamic settings. I know they're popular around here. But the idea is you have, say, perhaps Google is selling the new Pixel, and the buyer is looking at buying this phone, but they know that Google's probably going to come out with a Pixel 3 a year or 2 from now. And if Google offers some sort of contract up front, where you pay a bit more, you can get the second phone, or the third phone, I guess, in the future for less, right? And then the buyer will be willing to pay more today in exchange for a discount in the future. All right, so it's known that you can get more revenue by doing this sort of thing. All right, but we show that you really need to know the buyer's weighting function in order to do this sort of trade-off between future utility and present payments. All right, so there's no robust approximation, no constant approximation, even when these weighting functions are bounded by some constant.
Oh, that's nice. Because the thing that they sorry.
No.
That inherently depends on randomization, because this mechanism inherently depends on the buyer reasoning about the future. So there's no way to do that deterministically somehow.
So our mechanism is going to be deterministic. So we're only going to talk about deterministic mechanisms here.
Mm-hmm.
But the buyer still has some uncertainty about her future value. So there's some inherent randomness that the seller cannot control.
I see.
So the lower bound applies for all mechanisms, right? Like, it's not specific to. This is the lower bound is for 2 periods, 1 buyer, 1 seller, right?
Yes.
And it applies to both deterministic and randomized, or?
I'm not sure that applies to randomized. I suspect that there is also a lower bound for randomized mechanisms, but that
Okay, so you're
becomes
comparing
harder
the
to
space of
analyze.
deterministic mechanisms to the optimal
Yes.
deterministic benchmark,
Yes.
right? And the previous result was your mechanism compared against the optimal randomized mechanism.
Mhm. Yes.
After YF is randomized mechanism there.
Yeah.
Okay.
For risk neutral buyers.
For risk neutral buyers.
So there was no work on this for risk-averse buyers at all before our.
No, what do you mean by risk neutral? The benchmark is opt of Y, F, right?
Yeah.
Which is.
Yeah.
Okay.
All right, so here's a summary of all the results I just mentioned. So for the rest of the talk, I'm first of all going to explain the model in a little more detail, and then I can run through these results, giving a high-level overview. If there's anything in particular that you want to talk about or hear more or less about, let me know. Otherwise, I'll just sort of go through this stuff. Okay. So here's our model. So as I mentioned,
we have a question for you.
Yeah.
So the theorem, the result is on the best response. You give your announcement mechanism, the buyer best response based on his own Y. It's not necessarily the question. Not as I see in the sense there is a menu and he picks the best elements in the menu.
Yeah, we think of this as a menu. So
right. Then the second menu can depend on the first choice.
Yes. Right. Okay. Yeah. Yeah. So in general, for this setting, we think of deterministic mechanisms. So in other words, there's a menu of prices on the first day, and then depending on the price you choose on the first day, that determines what the price on the second day will be.
3 of the two in the menus.
Yeah. Yeah.
Okay. So one final question on this. So this result, the first theorem's result is for Y being convex functions, but any convex function is fine, right? Beta bounded convex function.
Any convex
function. Okay. And then for the utility functions, what do you assume?
Basically, it's just linear, I think, right?
Linear, yes.
Linear, both the benchmark and
yes.
Yours. Okay.
Okay, so we assume a linear utility function. We make assume that this is a convex, Y is a convex function. And then, so now we need to describe how this model generalizes to these more complicated lotteries, right? And the basic intuition is that we want it to satisfy an additivity axiom. Really, we want this for the dynamic setting when we want to look at the utility across the two stages, okay? So let's look at this example. So suppose that you're offered either $1, $2, or $3 uniformly at random. Now, the observation is that in each case, you're going to get at least $1, right? So your utility should be at least 1. Now, the second dollar comes with probability 2/3. And the third dollar with probability 1/3. So we want this to be the expected value for this whole random outcome should be 1 because you're going to get with certainty plus the expected utility of a second dollar with probability 2/3 plus the weighted expectation of a third dollar with probability 1/3. Okay. And this might be a little bit confusing. So the way to think of this is in terms of the cumulative distribution function, right? So here's the CDF of this lottery. And it's a standard identity that the expectation is equal to the area above the curve here, right? And now all we've done here is we've just transformed this CDF by raising these cumulative probabilities, right? And the formula that we use is exactly this. So think about this. If Y is the identity function, this 1 cancels that 1, and we get back exactly this FFC. Okay. So is this clear how this transformation works in this example? All right, now in general, we do exactly the same thing where we transform the cumulative distribution function. Here's the formal definition. Really the only new part is that when you look at negative values, okay, you subtract off the area below the curve to the left of 0. So this is exactly the standard definition of expectation. In our model, we just transform the curve in this way, and you can see that this negative area increases, the positive area decreases, so the weighted expectation is less than the mathematical expectation. All right. All right, so that's the model. Any questions about the model itself? Okay. All right, so in general, we're going to say that a mechanism is defined by this menu of pairs. So X and P, where X gives you the allocation, and we're only going to look at ex post deterministic, or I should say ex post full allocation. So either you get the item or you don't. There's going to be no fractional allocation. All right, and then we assume that the payment is just some arbitrary payment. And the buyer is going to select the pair or the distribution over allocation and payment, which maximizes this weighted utility, expected utility. All right, but whereas in a risk-neutral setting, the distribution you can assume is just over, what the probability of receiving the item is. Here, because we're looking at this whole transformation of the entire CDF, it really matters what the distribution over X and P are. So for in particular, it could be the case that, for one particular pair from this menu, even conditioned on receiving the item, there might still be some randomness in the payment. All right, and that's different from just looking at a 2-outcome lottery where your payment is one thing and you either receive the item or don't. Okay, so we really need to understand what this looks like. All right, so let's look at this simple lottery where either you receive the item and you pay P, or else you get nothing and pay nothing. Now, there are really 2 cases to look at. First, sorry about that. So suppose your value is less than the price. Then when you actually receive the item, when you are allocated, your utility is negative. So this is the transformed CDF, but with the transform probability here, you get this negative utility. All right. And so this subtracts. And note that as your value increases, the width of this rectangle decreases, and your utility changes exactly this rate. So you get this linear function. And then when your value surpasses the price, now when you receive the when you actually get the item, your utility is positive. And now we're looking at the area above the curve here. And so the weight here is y of x. So there's actually a bend in the utility function when you go from negative to positive. All right. And we call this type of lottery a binary lottery. So we're going to show that the optimal mechanism always consists of these sort of simple binary lotteries. All right. Are there any questions about this example before I move on? It's not too critical to understand it exactly. The main thing to remember is that for the simple binary lottery, we get a curve that looks like this, which has slope equal to the weighted probability of allocation. And in general, we get some concave utility curve. OK. Now going back to the mechanism, remember that the mechanism is this menu of these pairs. And in general, the buyer is going to pick the pair which maximizes this weighted expectation. So you get some sort of curve, which looks like the max of all these individual utility curves. And for a risk-neutral buyer, we know that this function, this utility curve, is convex because you're just taking the max of all these linear functions. In our case, because these functions are now concave, the utility function of an individual lottery is concave, you might get some non-convex utility curve for the menu. All right? But we can actually show that the optimal mechanism has a convex utility curve. So we can do this by taking the convex envelope, so just the maximal convex function, which is upper bounded by this original curve. And then we find a menu of these binary lotteries, which produces a utility curve that's exactly equal to the convex envelope. And we can show that you actually don't lose revenue by switching from the original menu to this simpler menu. All right, and I'd be happy to talk about the details, but in the interest of time, I'll probably skip them. But I have some nice slides, actually, that give the intuition, but I don't think I'm quite have time to go over it. So. OK. So how
this probably uses this theorem that the optimal mechanism will induce a convex utility curve uses the convexity of y, or no? It doesn't depend.
It does use it. I don't think the intuition doesn't really depend on it. Okay. There's sort of some details where we use convexity, but so I think you could eliminate convexity from this with some more careful analysis, but I'm not sure. Yeah, the basic idea is that as long as you have sort of a risk-averse buyer, some complicated menu is has a lower utility than a binary lottery that allocates with the same payment and has the same expected payment and allocation probability. So if you sort of eliminate reduce the uncertainty to as little as possible, you should only increase the utility, and then you can take this convex curve. You can actually show that the curve has a higher payment and allocation probability than that sort of simplified. That's the very hand-wavy, vague explanation, but that intuition doesn't depend on convexity in any way. OK, so how do we make more revenue? So here's the basic idea. Suppose you have a risk-neutral buyer. You offer a price. That gives you this utility curve here. Now, if you add a second lottery with a lower price, some non-certain probability of allocation, then buyers whose values lie between this lottery price and the original price will now purchase the lottery, so you're going to gain some revenue from them. However, there'll be some buyers up here who would have previously purchased the item at the price, and we're now going to switch to the randomized lottery. And since we know that the optimal mechanism is deterministic, we know that the gains from these buyers are going to be canceled by the losses from those buyers. However, for a risk-averse buyer, you can offer exactly the same price in lottery, but because people undervalue this lottery, fewer people switch from the price to the determinant, from the price to the lottery. So you actually lose less from those people who switch, but you gain the same amount from the people who were previously buying nothing, right? And as the risk aversion goes to extreme in some sense, basically as you become arbitrary, you have an arbitrary small weight for a probability that's just below 1, then you can basically just add these lotteries, one for every value, and everybody's willing to pay as much as possible, so you have a get the item as much certainty as possible. Okay. So the point of all this is just that we can characterize these mechanisms according to this allocation rule, which gives the allocation probability for this binary lottery. We get a payment identity out of this by looking at this convex utility function. And it looks very similar to the risk-neutral setting, except that it's not quite the same. This payment identity has these nonlinear weighting functions in it. However, this is still useful for further analysis because we can use this weighting function, or sorry, this payment function to compare the optimal mechanism for a certain risk-averse buyer. And then basically the idea is that we can relate that to a risk-neutral buyer, relate it to a mechanism for a risk-neutral buyer, which we know is upper bounded by price. And then we can upper bound the revenue from this randomized lottery for a risk-averse buyer by the optimal revenue for price, obtained by price. Okay, so that's all I have for this one-shot setting. So the dynamic setting, So the setting is exactly that we have one buyer, 2 items. We know a distribution over the buyer's values. The buyer doesn't learn this second stage value until after having made a decision for this first stage mechanism. And the seller can offer a mechanism that depends on the buyer's choice in the first stage. All right, so we're also going to assume that the mechanism is deterministic, which means that it's a price in each day. And we're going to assume that the buyer is ex post individually rational, meaning that she won't pay more on any stage than her value for that stage. All right, so here's this example that's fairly common. I don't know how many of you are familiar with this. Mm-hmm. Some of you, some not. Yeah, okay.
I've used this example. We both have used this example many times, actually.
Right, so the point is that you have this distribution where if you just set a price on each day, no matter what price you set, the revenue is going to be 1. All right, so this is called an equal revenue distribution. However, we can set a pair of prices such that the utility that the buyer expects to receive on the second stage is exactly equal to the price that she pays on the first stage. All right, and then every option in this menu has exactly the same utility. So we just assume that the buyer is going to pay her value, right? And then you get revenue that's at least equal to the buyer's value on the first stage, which can be much larger than 1. All right, but this should be somewhat off-putting because we're assuming that the buyer is, indifferent between all of these different options and is just going to be willing to pay her full value on the first day. All right, and we show that if the buyer is risk-averse, well, if we actually know the buyer's weighting function, you can recover exactly the same sort of result. Okay, you can basically recover the full, not quite the same full value on the first stage, but something that is like the minimum of the buyer's first stage value and the weighted expectation of the second stage value. Right? But if you don't know this weighting function, we can come up with an example where no mechanism can give a constant approximation, even though the weighting functions are a class of functions that are 1/8 bounded. So they fall within some reasonable range for risk-averse, for uncertainty-averse buyers. Okay, and I can talk about this in more detail. I hadn't prepared to talk about it, but since some of you are somewhat experts on this, I can go over it a little more. This is definitely the most technical part of the paper.
Again, this is for, in this class, this lower bound is for convex Y, right?
Yes. Yes, there's some convex Y up there.
Can you give some intuition why this is true? Because it can come up with distributions that are very, the distributions can cause very little value for some Y's and very high value for other Y.
Yeah,
It's,
right.
but
So the point is that for a risk-neutral buyer, you need to extract a lot of revenue on the first stage. So you have to offer prices that cover a wide range of first stage values. Okay, but in order to do that, you have to give a decreasing second stage price, right? As your value on the first stage increases, you have to be promised a smaller and smaller price on the second stage, right? But a very risk-averse buyer, or even not that risk-averse, like some, beta-bounded for some constant risk-averse buyer, basically, in order to get them to pay their full values, you have to offer a steeply discounted price on the second stage. And so these things are sort of in conflict. So for the risk-averse buyers, you have to offer the steeply discounted price. For a risk-neutral buyer, you have to cover a wide range of first stage values. So you have to have a wide range of prices on the second day. And you just run out of discounts on the second stage.
Wait, so are you saying that your class of Y is just risk neutral plus one particular risk averse?
No, so we actually needed, we looked at a continuum of weighting functions.
so just the risk averse and the risk.
Yeah, we couldn't come up with a way to make it work with just like a finite number of
Just the extreme
weighting functions. Yeah. So if you want, I can sketch a little bit on the whiteboard if you're interested in seeing more. So, how am I doing on time here?
We have 10 minutes.
Okay. So, let's look at it like this. So you have some first stage price, E, and you're going to want buyers to purchase this exactly. So you offer some utility for the second stage, right? And for a price of 0, you can offer 0 second stage utility. And then you want people to keep paying their value. So the utility has to increase exactly proportionally to the price, right? So this means that the utility is exactly equal to the price, so they cancel each other out, and your effective price is 0. The point is that as this increases, though, at some point you hit the utility that you could possibly, the utility that corresponds to offering a price of 0 on the second stage. So this has to flatline at some point. You can't go on offering more and more utility on the second stage. Right? And then what we do is we show that, so this corresponds to setting a price of 0. So we'll call this U of 0. And then your expected revenue is equal to either your value up until this point or this value thereafter, right? So you can get something like one.
So the seller is still quasi-linear as well. So the seller is.
Yes, so the seller is risk neutral.
The seller has the same. I'm not sure if that makes sense. The question.
Because one problem is that you have disconnect between the risk profile of the seller and then the buyers.
But usually papers are like that.
Yeah, people are like that.
Either the seller is risk-averse or the buyer is risk-averse.
I wonder if you can actually get something both the same. The problem is that they're the same. The problem is that they're unknown actually, which doesn't make sense. If it has the same as you and
So
you
there
don't
was
know
a
it.
paper by Chichi and Mukund, which was very similar in spirit for sellers, universally approximating all
For all the sellers.
all seller risk profiles. Basically.
I see.
It was a single mechanism that he can use.
For every seller's profile
Yeah,
gets
like a posted price based mechanism. But there they assume buyers are all like completely risk-averse.
Here buyers are risky.
Here buyers are risk-averse.
And
It
the
seems
seller
like
is
the
risk-averse.
more
That seems a natural case.
natural thing to do.
The seller is doing a bunch of things.
Yeah.
Yeah, so the point is that this should really be, I guess, subscription by Y. It's very, very large for a risk neutral buyer. So this point here is pretty far to the right, right? For a risk averse buyer, in order to get this slope here, you have to offer a very steeply discounted price. So you can look at a parallel.
Beta is your constant, but even that's not enough, right?
No. So actually the function we look at is like, so it's like x squared up to some point t, and then it just rises linearly the one after. This is like squared and then some linear function there. Yeah. Okay, so I should probably, I guess, wrap this up.
Maybe you finish. Do you have any sense of randomized mechanisms you can do?
Well, I mean, maybe you can do something, but there it becomes very difficult to analyze. I mean, this
Because
analysis
expectations
here
get too crazy.
Yeah,
That's
because
wise.
you've got both the buyer's uncertainty and the randomness in the mechanism, and it becomes hard to reason about. Okay. All right, so basically we can look at our results in two different categories. So for a single shot setting, basically we show that when the seller controls the randomness, so you control the randomness in the lotteries, you can use that to your advantage and you can extract more revenue. Right? But then there's dynamic setting where you have two stages. The uncertainty is inherent in the setting. It's inherent in the environment. The seller cannot come up with a deterministic mechanism that gives a constant approximation, regardless of, even when you assume that the buyer's weighting function belongs to one of these realistic classes of weighting functions. All right, so there's a lot more work that we can do here. So we didn't actually find the optimal mechanism, even computing it just for like a really simple example, like uniform 0, 1, y equals x squared. Don't really know how to compute the optimal mechanism there. So that would be an interesting thing to do. Multiple buyers. It seems difficult to find the optimal multi-buyer mechanism, but for example, you could analyze posted prices. So something like this seems like an interesting direction. And basically anything you can think of for risk neutral buyers, it's unexplored in this prospect theoretic model. Okay, so I'll stop there, I guess. So any other questions?